Okay, good morning everyone. We're going to pick up with the Chapter 9 content on units of concentration. I think in the 2:40 afternoon lecture last week, we actually went over this stuff. So if you have already gone through this stuff with me, you can skip ahead to the next video. But if you have not, then you'll need to watch this. We introduced concentration back in Chapter 7 when we talked about K and the equilibrium constant. But we would need to thoroughly go over it here, and we're going to work several problems. So concentration is simply an amount of solute. Remember, this is what's being dissolved in the solution per a volume of solution. Okay, we usually express the amount of solute as a mass, so units of like grams or moles or things like that. Now this is important. You can see from this picture over here that especially nurses, different areas of health sciences, we administer different IV, drips, medication, nutrients, and we have to know the concentration of the things we're putting in the body. So this is critical to be able to calculate and convey units of concentration. There's two primary ways we do this. Number one, with a weight volume percent, we abbreviate that, WV percent, or we call it a mass volume percent. And to fill in the blanks here, the way we calculate this is we do grams of solute per milliliters of solution. Now this is critical, milliliters. Don't confuse that with liters or any other unit for volume. It's grams of solute per milliliters of solution times 100. Also, if I'm speaking too fast or moving too fast, the beauty of recorded video lectures is that you can pause, rewind, rewatch. So I am going to try to move relatively at a decent pace on this, just so that these videos are not 20 to 30 minutes long. But slow me down if you need to. Okay, the other way we calculate concentration is through molarity, and we abbreviate that with N. That's what we used in the equilibrium expression for K, was units of molarity. Here we have moles of solute, the thing being dissolved, per liters of solution. So keep the milliliters and the liters straight as to which equation they belong to. Again, molarity is critical. Nurses, when you calculate, we learn a lot of things from urine samples, and we can calculate the volume of water, the concentration of water, the concentration of salt, a lot of other things from urine. And so that's critical when we're, for example, when you're doing dialysis lab work with urine turbidity, to calculate concentration there. So we will do some practice problems with these equations in the coming slides, but there they are. Okay, how do you prepare a solution? There's actually a particular way. You have to remember that the volume of a solution, which contains your solvent and solute, I just said it, includes both solvent and solute, okay? Not just solvent. So the way you mix this, you have to remember that the solute has a volume too. So we're going to follow these pictures through left to right. Number one, you add the solute to your flask or whatever your container is that you're preparing the solution in. Then step two is you add some solvent and you mix it up. We do not want to add, say I wanted a one liter of some solution, a salt solution or whatever. I'm not going to just dump a liter of my solvent in because then I would probably have too large of a volume. It would probably actually be above 1 liter slightly, which might not sound like a big deal to you, but your concentration would then be incorrect. Okay, that's why you add some solvent, dissolve or mix your solute in, which is what they're doing in the second picture, mixing it together. Then 3, add solvent to final volume. Okay, then you're going to add the rest of your solvent until you get the final exact volume that you want, so that your concentration is exact. Moving on, oh, by the way, so if I ask you how do you prepare a solution, I would want you to walk me through these steps. Moving on, remember I said solutions can be not just a solid dissolved in a liquid, although that's most common. They can also be solid solutions, okay? For example, a mixture of gold and copper, these are both solids. And I don't want you to get too into the units or the math here. I just want you to know, because we have two solids and we don't have a liquid, essentially we would convey this as a weight per weight percent, okay? Instead of a weight per volume percent. And you would then convey units as grams of, your solute per milligrams of solution times 100, okay? The point being here that both of these units are units of mass, not mass and volume. Same idea down here, dissolving one liquid in another, we would have a volume per volume percent. Okay, I think there's a really good textbook problem that I'll probably give as a practice problem when we get closer to exam 4, that you will actually calculate a volume per volume percent instead of a weight volume percent. And that is just one liquid mixed in another. Here you're going to have units of, we'd probably do milliliters of solute per milliliters of solution. Okay, that seems confusing. The units actually do cancel out and work out here because your percent never has units on it. It's just a percent. But I just wanted to introduce that idea to you. Okay, we're going to work a couple problems with the weight volume percent equation. And then there's several we're going to do here. I'm just going to work these two on this first slide, 1 and 2 here. And then I think 3 and 4 down here, we'll number these 3 and 4, are great practice problems for you to attempt on your own. And then I'll probably put them on some sort of review for exam 4 because I'm not working them right here. And then we'll skip ahead. I'll work this molarity problem, and that'll be the end of this video. And then the next video we'll pick up with molarity as a conversion factor. So number 1, I'm going to turn my screen sideways so that you can walk through this with me. What is the concentration in weight volume percent of a 15 grams of glucose dissolved in 100 milliliters of solution? So there's our equation. We're going to plug in the pieces we don't have, and we're solving for the percent. So I'm going to plug in my grams of glucose, I'm going to plug in my milliliters of solution, times by 100, get my weight volume percent. So it should be like this. Weight volume percent equals 15 grams, I'm going to do capital G for glucose, divided by 100 milliliters of solution, times 100. What is my weight volume percent? So 15 divided by 100 times 100. Notice that the hundreds will actually just cancel out. And then your weight volume percent would just be 15%. Okay. Now, when we say weight volume percent, notice the units are actually in here. Weight is the units of the grams, volume is the units of the milliliters, because that's what you have over here, right? You have grams on top, you have milliliters on bottom. You're like, well, those don't cancel. They don't just go away. You could write it as, where's my red? Okay, you could write it as 15 gram per ml percent, okay? But when you convey a percent, it's understood that the gram and the milliliters are in there if you're conveying a weight volume percent. So you actually don't have to write the grams and the milliliters in there. You just would write the 15% solution, okay? Because everybody should know this definition for weight volume percent. Okay, that's number 1. Number 2, if we dissolve 180 milligrams, notice we have units of milligrams, not grams. So we're first going to have to convert to grams, all right, before we can plug in. We're going to dissolve 180 milligrams of heparin. Anybody know what heparin is? Y'all can't respond right now, but I would ask this in lecture. It is an anticoagulant. It's part of your blood clotting system. I did a lot with heparin in grad school in my research and stuff. But we're going to dissolve that into 15 milliliters of aqueous solution. What is the weight volume percent? So we need to do step 1. Convert 180 milligrams to grams. So I have 180 milligrams. I'm going to abbreviate heparin. The question is, how many milligrams are in 1 gram, or however you want to do this. Some people do it different ways. You figure out how many grams are in a milligram, but you just need to plug in that relationship. If you remember, we've covered this way back early in the semester. There is 1,000 milligrams in 1 gram. So what should happen to units here? Milligrams cancel. 180 divided by 1,000 equals 0.180. Now this is grams of heparin. Okay, and this is what we'll plug into our equation. So now our weight volume percent is equal to 0.180 grams of heparin on top divided by 15 milliliters of solution on bottom times 100. So when you do this, it works out to 0.18 divided by 15 times 100. I got a 1.2% solution of heparin. Okay. These are relatively easier examples, which I wanted to start with the easy examples. Now, these down here, you're not solving for the weight volume percent. Here, it's asking you how many grams. So here, you're solving for the top portion of the equation. So you need to rearrange your equation. We've done this multiple times with things like specific heat when we're solving for different portions of a equilibrium expression. You should be familiar with how to rearrange or cross-divide, cross-multiply. And then down here, it's asking for how many milliliters. So number 4, you're actually solving for, number 4 is asking you to solve for the milliliters portion. Number 3 is asking you to solve for the top portion. So these are a little more challenging because you're not solving for the percent. You're given the percent. Keep in mind the 100 over here, and then you'll solve for other portions of the equation. But I want you to attempt those. Again, we'll go over these on a review before the exam. All right, lastly, let's work this molarity problem, and that will be the end of this video. So molarity, remember, is moles of solute per liters of solution. Here is our problem. We dissolve 2.335 grams of H2SO4, that's sulfuric acid, or you could call it hydrogen sulfate, in water, and we dilute it to 50 milliliters. What is the molarity? So we have to plug in moles and liters. We are not given moles or liters. So what do we have to do? We have to convert from grams to moles. How do we go from grams to moles? Do you guys remember? This was chapter 6. We use a molar mass. So we have to calculate the molar mass of H2SO4. And then we'll have to convert from milliliters to liters, all right, as well. And then we can plug those things in and get molarity. So there's some extra steps on the front end so that we plug in the right units. So I am actually going to do a quick check on our molar mass. You should remember how to calculate it, but I'm just going to look it up really quick. Molar mass of H2SO4. And it is 98.078. So the molar mass is 9 grams per mole. So we're going to take 2.335 grams of H2SO4 and convert that to moles. So 98.079 grams on the bottom per 1 mole on the top. So 2.335 divided by 98.079, and you should get 0.0238 moles of H2SO4, and this is what we'll plug in on the top. All right, and then 50 milliliters, we'll do this part, 50 milliliters, convert that to liters, so there's 1,000 milliliters for 1 liter. So 50 divided by 1,000 should be 0.05 liters. Now we can plug in moles on the top, liters on the bottom. So our molarity, capital M, equals 0.0238 moles over 0.05 liters. And I got that our molarity is or our solution, I'll write it this way. Our solution is 0.476 moles per liter.